All right, so in order to do this calculation, we really only need two main concepts. The first one is the Stefan-Boltzmann Law, which allows us to relate energy transfer or heat transfer to the temperature of an object. Second thing we need is just some basic geometry of circles / discs and spheres. Okay, so first, Stefan-Boltzmann Law. We can say the heat transfer, energy transfer, is equal to, we're going to have 4 pi multiplied by the radius of the object times the Stefan-Boltzmann constant. It's just a number, and then temperature to the 4th power. Okay, so that is our Stefan-Boltzmann law. And then, of course, for the area of a circle, or a disk, we're going to have pi r squared. The area of a sphere, it is 4 pi r squared. All right, first thing you should do anytime you are working on a physics problem is draw a pretty picture. So we're going to start with the sun. There we go, which has radius. Let's call that r sub circle dot. That's the typical symbol used. Some distance away, we will have the Earth. Call that distance d. Of course, this is not to scale. Okay. And the Earth will also have some radius. Let's call that r circle cross. It's the typical symbol. And the Earth will orbit around the sun at that distance. All right. So this is a two-dimensional view. But of course, the sun is radiating in a three-dimensional sphere. So if we wanted to look at, how much, how is the radiation distributed across a sphere at the with a radius at the distance of Earth's orbit. Okay, so the total surface area of a sphere around the sun at the orbit of the Earth, let's call that distance d there, would be 4 pi d squared. Right? Of course, the Earth is not actually absorbing all that radiation because it is not completely surrounding the sun. It is only going to get whatever the cross section is of the size of the Earth at that distance. So then we need to consider a disk where the Earth is of some surface area. Okay, so surface area Earth, have pi, radius of the Earth, squared. So now we need to consider what percent of this total area does the Earth actually take up. So let's just call that a percent, but of the Earth's area compared to that total surface area of the sphere. we're just going to divide these two equations, right? So with the Stefan-Boltzmann Law, we can look at the heat that Earth will receive as H Earth times not just the total output of the sun, but whatever that percentage here is times the actual heat output of the sun, which using Stefan-Boltzmann Law, we can rewrite this guy as we have. Let's do a little bit of simplification here. So a pi will get crossed out on either one of those guys. And then also we can recognize that 4 is 2 squared. So let's just rewrite the percentage part here, all under 1 square. Okay, and then for the sun's output, radius of the sun squared, Stefan-Boltzmann constant, temperature of the sun to the 4th power. Okay, so that should be the flux absorbed by the Earth, right? Now, to find the temperature of the Earth, let's consider now the Earth as a black body that is going to re-radiate, not as a disk, but as a sphere, kind of like how we treated the sun here. So we're going to say that this here is equal to 4 pi, this time radius of the Earth, squared, Stefan-Boltzmann constant, temperature of the Earth to the 4th. And this is what I promised would solve for, temperature of the Earth here. So let's deal with this equation. For one thing, we have a 4 pi both sides, so we can cancel that out. What else do we have? We have Stefan-Boltzmann constant that can cancel out on both sides. We have a radius of the Earth squared, which we can cancel out. All right, so quite a bit has canceled here, and actually we're just left with temperature over on this side to the 4th power, of course. So let's just take the 4th root of everything on this other side here, and I'll write it over here. We don't unnecessarily waste another piece of paper. So 4th root. Make sure we have plenty of space there. All right, what do we have here? Well, we hung on to a radius of the sun squared. We hung on to a temperature of the sun to the 4th power. And then down here, what do we have? We have a 2 squared, right? I'll rewrite that as 4. And d squared. Now, this actually simplifies. You might recognize if you take something to the 4th root, that's like to the 1 over 4th power. So if you have a 2 over 4th power, right? 2 divided by 4, that's the same as 1/2, right? So we can simplify this to just going with 1 square root, and also this is to the 4th, so that'll come on out. So we have temperature of the sun times the square root of what remains in here, and we are taking a square root, so that'll go back to 2. And that is actually the answer, okay? And so something fun we can do now is plug in some numbers to that. So I already went ahead and a while back tried plugging in some numbers for various planets. So first, Earth we could look at. If we plug in the temperature of the sun, the radius of the sun, distance between Earth and sun, we're going to get around 278 Kelvin. All right. I think that's somewhere around like 40 or 50 degrees Fahrenheit, but that's pretty close. It's minus 10 Kelvin from the actual average temperature of the Earth, which is 288 Kelvin. So, we made a lot of approximations. For example, assuming everything absorbs and emits perfectly, which of course is not true, but it gets you pretty darn close to the correct answer here. Some other planets you could look at, Mercury is the first one up top there. Pluto, surprisingly close there, 43 and 44 Kelvin. So for a very simple derivation, it's quite powerful.